In this video, we want to learn about the matrices and the matrix operations. Let's start with the definition of a matrix. A matrix simply is an array of numbers. And the numbers in that array, we call them elements of the matrix or the entries of the matrix. Let me show you an example of a matrix. 2, 3, 5, -1, 0, 4, 1, 5, -2, 3, 2, -1. This is an example of a matrix. And as you can see, usually we show this array of the numbers with capital letters. So usually we use capital letters to denote the matrix. For example, we use letters like A, B, C, D, and so on. Every matrix has a size. But what is the size of a matrix? The size of a matrix is the number of rows and the columns of that matrix. For example, here we have a 3 by 4 matrix because in this example we have 3 rows, as you can see, and we have 4 columns. So the first number always shows the number of rows, and this second number shows the number of columns of the matrix. Usually we write the size of the matrix here or here. So this is an example of a 3 by 4 matrix. This matrix in total has 12 elements because this is 3 rows, 4 columns. 3 times 4 is 12. And so this matrix has 12 elements or 12 entries. Each of these numbers are one element of this matrix. Every element of a matrix has an address, and by having the address we can locate the position of that element. For example, consider this element here, 5. This element is located at the first row, third column. So if we want to talk about that element, we say A sub 1, 3. The first number refers to the row and the second number is column of that element. And note that when we want to talk about the elements, we use the lower letters. Because the matrix is capital letter A, we use lower letter A to talk about the elements. And this element, the first row, third column, is 5. For example, what is the element in third row, second column? Can you find this element? The element that is located in third row, second column, at the intersection of the third row, second column, is 3. What is the element at second row, fourth column? Can you find this element? Second row, fourth column. What is that element? That element is 5. What is the element at second row, first column? Second row, first column. It's 0. Now we are a bit familiar. What is a matrix? What are the elements of the matrix? And as you can see, for a matrix, we have a dimension, the size of the matrix, which usually we write it here. We show the matrix by capital letter and we show the elements by lowercase letters. Now let me show you some more examples of a matrix. For example, consider this matrix. Matrix B is 3, 2, 1, negative 1, 0, 10. This matrix, what is the size of this matrix? Whenever you look at the matrix, immediately figure out the size of the matrix because it's important. This matrix is a 3 by 2 matrix because we have 3 rows and 2 columns. Let me show you another example. Look at this matrix. Negative 1, 2, 3, 0, 1, 2. What is the size of this matrix? 2 rows and 3 columns. So this is a 2 by 3 matrix. Let me show you some more examples. Consider this matrix. Let's name it D. 1, negative 1, 2, 4. As you can see in this matrix, we have only one row, but we have 4 columns. So this is a 1 by 4 matrix. And because this matrix is only one row, sometimes we name it row matrix or row vector. Later in this video we will learn about vectors, but if you right now you are familiar what is a vector, probably you understand why they name this vector, because actually vectors are a matrix that is only one row or one column. But it's not the topic of this video. Anyway, when we have one row, we say the matrix is row matrix. Probably you can guess that we can have column matrix. Let's name it E, or I prefer to name it C because column matrix. Why not? Let's name it C. For example, negative 1, 2, 3. This is just one column but 3 rows. So this is a 3 by 1 matrix. And of course, we name it column matrix or column vector. The next important matrix, this type of matrix is very important, is a square matrix. A square matrix is a matrix that the number of rows and the number of columns is the same. For example, negative 1, 2, 3, negative 2. This is a 2 by 2 matrix, and we say such matrix a square matrix. Let me show you another example of a square matrix. Let's make it 3 by 3. Negative 1, 2, 0, 0, 4, 0, 9, 1, 4. This is a 3 by 3 square matrix. And a square matrix is really important in linear algebra. Later we will learn why they are really important in linear algebra. But for now, remember, a square matrix is when the number of rows and columns is the same. Now that we know what is a square matrix, let's talk about the diagonal, or actually main diagonal of a square matrix. What is the main diagonal of a square matrix? These elements make the diagonal of a square matrix. And only we talk about the diagonal of a matrix if we have a square matrix. If we have a matrix like this, 1, negative 1, 2, 3, 4, 5, we don't have any diagonal here. It doesn't make sense to have any diagonal. Only we define diagonal for a square matrices. For example, in this matrix, this is the diagonal of the matrix. So -1 and -2 are the elements of the diagonal of this matrix, and -1, 4 and 4 are the elements of the diagonal of the matrix F. So now we know the definition of the main diagonal of a matrix. The elements that are located at position 1, row 1, column 1, row 2, column 2, row 3, column 3. These are the elements of the diagonal of a matrix. Now that we know the diagonal of a matrix, let's talk about three important square matrices. Consider a matrix like this. I use letter U here because I have a reason for that. Consider this square matrix: 3, 2, -5, 0, 4, 9, 0, 0, -2. What is the diagonal of this matrix? These are the elements of the diagonal, and this is the diagonal, or actually main diagonal of this matrix. As you can see here, probably you have noticed, all the elements below the diagonal of this matrix are 0. Actually, the matrix is only in top because below the diagonal is only 0. We don't have any non-zero term below the diagonal. When we have such matrix, we say this matrix is upper triangular matrix. So in upper triangular matrix, all the elements below the diagonal, main diagonal, is 0. And I use letter U because this U can be abbreviation for upper triangular matrix. You can name it anything you like. It doesn't matter to name it only U. Probably you can guess that we can have lower triangular matrix. Let me show you an example of lower triangular matrix. Consider this matrix: 1, 0, 0, 2, 4, 0, 0, 9, 5. As you can see in this matrix, let's name it L. All the elements of this matrix that are above the diagonal are 0. All of these elements are 0. So we name this matrix lower triangular. Note that what is important for us in lower triangular, to have the elements above the diagonal to be 0. It doesn't matter if we have 0 here. It's completely fine. This is lower triangular because the elements above the main diagonal is 0. Now let's talk about another important square matrix, and that is the diagonal matrix. What is a diagonal matrix? Can you guess what is a diagonal matrix? A diagonal matrix is a matrix that all elements except the elements on the diagonal are 0. Let me show you an example of a diagonal matrix. Let's name it D. Why not? Diagonal matrix. Name it D. 4, 0, 0, 0, 3, 0, 0, 0, -1. This is an example of a 3 by 3 diagonal matrix. In the diagonal matrix, all the elements above the diagonal and all elements below the diagonal are 0. Actually, a diagonal matrix is lower triangular and upper triangular because the elements below and above the diagonal are 0. So now we are familiar with a square matrix, upper triangular matrix, lower triangular matrix, diagonal matrix. And you have to keep these in your head. For future, we need these type of matrices. Now let's see what is the identity matrix. Identity matrix is probably the most important matrix, and probably, as you can guess, we show it with I. So whenever in linear algebra you see capital letter I, probably they mean identity matrix. Identity matrix is a diagonal matrix, so it's important to be diagonal, which means that above the diagonal and below the diagonal we have only 0. But in identity matrix, all the elements in diagonal are 1 and the other elements are of course 0. So the difference between identity matrix and the diagonal matrix is that in identity matrix the elements in diagonal are only 1. Let me write for you an example of a 3 by 3 identity matrix. 1 0 0 0 1 0 0 0 1. This is an example of a 3 by 3 identity. Let's write the 2 by 2 identity matrix. 1 0 0 1. But why this matrix is important? What makes this matrix important? Later we will learn more about the importance of this matrix, but for now, remember that the role of identity matrix in linear algebra is similar to the role of number 1 in algebra. 1 is one of the important numbers, maybe the most important number. Why this matrix plays the role of 1? What is this relation? If you remember from algebra, 1 times by any number equals that number. We know this. 1 times by 2 equals 2, 1 times 10 equals, and 1 times x equals x, which x is in any number. Identity matrix has the same role here, which means that if we multiply identity matrix by any other matrix, say A, of course if we can multiply it. Later we will learn how to multiply two matrices, but for now suppose you know how to multiply. If you multiply identity matrix by any matrix, or if you multiply that matrix by I, doesn't matter the order here. The order of multiplication in matrices matters, but for this case no. Anyway, if you multiply the matrix I, identity matrix, by any other matrix, the answer is again A, which means that when you multiply the identity matrix in any matrix, nothing changes. Like 1 times x is x, I times I is A. That's the reason I'm saying this plays the role of number 1 in algebra. So, of course, it's important in linear algebra. Don't worry if you don't know how to multiply two matrices. In the next video, I will show you how you can multiply two matrices. Let's continue learning about important matrices. So far, we are familiar with different types of matrices. Another important matrix is the zero matrix. What is zero matrix? Probably you can guess. Zero matrix is a matrix that all the elements are 0. It can be a square or non-square. It doesn't matter to be a square. Identity matrix is always a square, but zero matrix can be of any size. It can be 2 by 2, 2 by 3, 3 by 5, 5 by 7, whatever. Let me show you a 2 by 3 zero matrix. As you can see here, all the elements are 0. And let's show it with symbol O. Why not? This is a 2 by 3 zero matrix. Let me show you another zero matrix. 0, 0, 0, 0. This is a 2 by 2 zero matrix. So zero matrix is simply everything is 0 in that matrix. Now that we are a bit familiar with different type of matrices, let's talk about when two matrices are equal. Two matrices are equal if the size of those two matrices be the same and all corresponding elements also be the same. So, for example, consider this matrix -1, 2, 5, 3, 1, 1. This is a 2 by 3 matrix. A second matrix equals to this matrix if all the elements, first of all, if the size be the same, so this should be 2 by 3. And also the elements of this matrix should be exactly the same as that matrix. So which means that only we can have -1 here, 2 here, 5 here, 3 here, 1 and 1. So it's obvious what it means that the two matrices are the same. If all the elements be the same, the size be the same, everything be the same. This means the two matrices are equal. Now let's try one example. Find the values of A, B, C, and D such that this matrix 2, 3, -1, 5 be equal to this matrix A plus B for A minus B, C plus 2, and finally D squared plus 1. We want to find the values of A, B, C, D such that this matrix be equal to that matrix. We know that two matrices are equal to each other if every element that appears here appears in the second matrix. All the elements, all the corresponding elements be the same. First of all, the size of these two matrices is the same, which it should be. And now A plus B must be equal to 4A minus B, 3, C plus 2, -1, and D squared plus 1 equal 5. Now from these equations we have to find A, B, C, D. Let's start with C, which is simple. From this equation, if we move 2 to the other side, -1 minus 2 is -3, so C is -3. From this equation, we have D squared equals 4. If we bring 1 to the other side, 5 minus 1 is 4. Because D squared is 4, if we take a square root, D equals plus minus 2. Now let's find A and B from these two equations. For finding A and B in these two equations, we can use substitution method, elimination method, or other methods. And later in this course, in linear algebra, we will learn other methods for solving system of equations. But for now, to solve this system of equation, these two equations, and find A and B, if you add this equation to this equation, we want to use the elimination method. If we add this equation to this equation, -b and b cancel each other. 4a plus a is 5a. So if we add these two equations, in the left side we have 5a and in the right side we have 5. 2 plus 3 is 5. So a is 1. Because a is 1, if we plug in 1 here for a, 1 plus b equals 2, so b is 1. So we can conclude that if a equals 1, b equals 1, c equals -3, and d equals plus or minus 2, then these two given matrices in this equation are equal to each other. Let's talk about adding or subtracting two matrices. How we can add two matrices or how we can subtract two matrices. First of all, the size of the two matrices should be the same. For example, if you have a 3 by 2 like this matrix, is a 3 by 2. We have 3 rows and 2 columns. only you can add this matrix to another 3 by 2 matrix. So the second matrix must be the same size, otherwise you cannot add them. 0, 4, randomly we are putting numbers here. The sum of these two matrices is again a matrix of the same size. Adding or subtracting two matrices is really simple. How we add them? Add the corresponding terms to each other. This is corresponding elements to each other. 3 plus 0 is 3. Negative 1 plus 4 is again 3. 1 plus negative 1 is 0. 1 plus 5 is 6. 2 plus 3 is 5. And 5 plus 1 is 6. So if we add these two matrices, we get to this matrix. Similarly, we can subtract two matrices. Let me show you an example. Consider this matrix, negative 2, 3, 1, 6. This is a 2 by 2, so the second matrix should be the same size. 4, 1, 2, negative 7. The answer is again 2 by 2 because the original matrices are also 2 by 2. To subtract the two matrices, just we have to subtract the corresponding entries. Negative 2 minus 4 is minus 6. Attention to this minus here. 3 minus 1 is 2. 1 minus 2 is negative 1. And 6 minus negative 7, 6 plus 7 is 13. So this is how we can add or subtract the two matrices. In the next video, we will talk about how we can multiply the two matrices. And it's a bit harder than adding or subtracting two matrices. It's not that easy. But for now, we want to talk about a special type of multiplication. How we can multiply a number in a matrix. Let's talk about multiplying a number in a matrix. For example, consider this number, negative 3. We want to multiply this number, negative 3, in this matrix. 2, 3, 5, 1, 0, negative 2. When we multiply a number in a matrix, we say we multiply a scalar in a matrix. Because this is a number, we say a scalar multiplication. If we want to multiply a scalar or a number simply in a matrix, we multiply that number in every element. So it's really easy to multiply a number in a matrix. Simply multiply that number in every element. So we have the same size matrix. This is 2 by 3. We have the same size. Negative 3 times 2 is negative 6. Negative 3 times 3 is negative 9. Negative 3 times 5, negative 15. Negative 3, 0, and 6. This is how you can multiply a number in a matrix. Let me show you another example. Suppose we want to multiply 1/2 in this matrix. Negative 4, 2, 0, 6, 1, negative 1. We have to multiply 1/2 in every element. The result is a 3 by 2 matrix. 1/2 times negative 4 is negative 4 over 2, which is negative 2. 1/2 times 2 is 1. 1/2 times 0 is 0. 1/2 times 6 is 3. 1/2 times 1 is 1/2, and 1/2 times negative 1 is negative 1/2. This is how we can multiply a scalar in a matrix or number in a matrix. So far we know how to add the matrix, subtract, multiply a scalar or a number in a matrix. Let's talk about something different for a matrix. The trace of a matrix. What is the trace? If we have a square matrix, so it's important. If we have a square matrix, if we add the elements of main diagonal, that is the trace of that matrix. And because the diagonal is defined for only square matrices, the trace can only be defined for square matrices. For example, this matrix has no trace, is undefined. What is the trace of this matrix? It's undefined because this is not a square matrix. Let me show you an example of finding the trace of a matrix. For example, consider this matrix. -1, 2, 3, 4. What is the trace of this matrix? Trace of A, trace of the matrix A, we show the trace with TR. Trace of A is -1 plus 4. Add the elements on diagonal. -1 plus 4 is 3. Let me show you another example. Consider this matrix. Let's name it B. 0, 1, 2, 3, 5, 0, -2, 1, -2. What is the trace of this matrix? The trace of the matrix B is 0 plus 5 plus -2, which is 3. Add the elements of the diagonal of the matrix. 0, 5, -2. This is how you can find the trace of the matrix. Before I finish this video, let me show you how in general we show in a matrix, because later in these videos, in this series of videos, and in linear algebra in general, we have to be familiar with these notations. So far we have learned that when we talk a matrix, usually we use capital letters A, B, C, D. We know that a matrix is an array, a rectangular array like this. This array has a size which usually we write here. Here M is the number of rows and N is the number of columns. So this matrix has M row and N rows. The numbers of this matrix are the elements or entries of that matrix. And we know that every element has an address. For example, consider this matrix. -1, 2, 3, 0, 4, 5, 7, 9, 10. What is the elements in the third row, second column? Third row, second column is 9. So as you can see, every element has its unique address. So easily we can locate and find the elements. The first element, which is here, is the element that is in the first row and first column. So the first element is A sub 1, 1, which this can be any number. The next element is A sub 1, 2. Note that we are still in the first row, but we move to the second column. So the address is A sub 1, 2. The next element is A sub 1, 3. And this goes till we get to the last column, which is the nth column. So the last column is A sub 1, n. The next row is A21, A22, A23, and goes till A2n. And the rows continues till we get to the last column, the last row. We continue writing rows till we get to the last row. What is the last row? The mth row. A sub m1, A sub m2, A sub m3, and this goes till we get to the last element, which is A sub mn. We use capital letters to show the matrix. We use lowercase letters like A, B, C, lowercase letters to show the elements of the matrix. Let me ask you a question. Consider this matrix: -1, 2, 4, 1, 6, 7. What is the element here that is, say, in third row? Let me change this to A. That is in third row, first column. Third row, first column. So A31, which we suppose it's here, is 6. What is the element in second row, second column? Second row, second column, A22. A22 in this example is 1. And before I finish with this video, I have to mention this. Because this is a big notation for a matrix, usually we use this shorter notation. We put squares like this, bracket like this, and we write A sub ij, which means that all of these elements, and in the right side below here we write m by n. So whenever you see something like this, this means suppose something like this in your head. Imagine something like this. So this is shorter notation for this big notation. I hope by watching this video you have learned a bit about matrices. In the next videos we will learn more about matrix operations and other important things in linear algebra. If you like this video, please subscribe in my channel, and thank you for watching.